Hi everyone, my name is Sean Park. I'm a PhD candidate at University of Texas at Austin. My talk's title is Lower Bound on the Optimal Feedback Rate for the Downlink Multi-Antenna Cellular Systems. We'll notify that this work is joint work with Professor Namin Lee and Professor Jeffrey Andrews and Professor Robert Hiss Jr. We'll start this talk by presenting some role of CSIT in the multi-antenna systems. The role of CSIT can be categorized as two big categories. The first category is enhancing the power gain. By using some kind of a beamforming like a MLT, aligning with the desired signal direction can enhance the its usual power, which has some SINL gain. The second category is a multiplexing gain. Its main role is by avoiding the interference for example, in the interior interference, it is an enabler to send multiple independent streams so as to get some multiplexing gain. So CSIT is indispensable for the power and the multiplexing gain. But in practice, unfortunately, it is well known that it is not possible to get a perfect CSIT because of the finite rate feedback capacity. So in conventional, we use the code book, which consists of, for example, 2 to the B, and find the optimal code book code word by measuring the power between the dot product between the desired channel and the code word, and they send only the index. There are two main limitations in these approaches. The first is the feedback delay, and the second thing is the limited feedback capacity, so as to we have only a CSIT with a quantization error. Actually, limited feedback is a kind of active topic over the few decades, and then it might be that the most well-known result is derived by Jindal. He claimed that the feedback rate should be proportional to a number of antenna n and logarithmically with the SNR. But applying this into the cellular networks, actually we can conclude that when the users located within the cell centers, we should use the high feedback link capacity, while the users are located in the cell edge, we rather use the low feedback link capacity, because well, the SNR is most likely to be determined by a user's location in the cellular network. So we can conclude that this prior criterion is useful for a single cell deterministic user location model. Now we are shifting to our look to a system level point of view. There are two key differences between this system level point of view and the single cell model. The first thing is the most significant performance degradation factor is now intercell interference. So SINR rather than the SNR is more proper metric. And the second difference is that well, each users are randomly located, so individual SINR per user is different due to the random user location. So there is no deterministic SINR. So unlike the single cell model. Our fundamental question is that what is the optimal feedback link capacity from this system level point of view? Here's the problem formulations. We define the net ergodic spectral efficiency consists of basically downlink rate subtracted by the uplink overhead. So this downlink rate consists of this is the monotonically increasing function of feedback bits B. And also, this expectations will be averaging over this channel fading and the user location in the random code book. And also, this uplink overhead is actually a monotonically decreasing function of B. And this TC implies that the number of downlink symbols that experience the same channel fading. So basically, when the coherence time increases, our feedback overhead decreases. So upon this net spectral efficiency, our target is to find the optimal feedback link capacity, which is the functions of pathloss exponent, and number of feedback bits, and the channel coherence time, and the number of antenna. One feature we should think carefully is that this optimal feedback rate is not a function of an individual SIR, because we are now looking the feedback at the system level point of view. Here's the system model we used. We assumed the downlink cellular network, and each locations of a BS and the users are modeled by a homogeneous Poisson point process. And the base station has n antennas, and user has a single antenna. And channel model we use the Rayleigh fading, and power law is the actually the distance with the order of inverse with the pathloss exponent beta. When you use the quantization cell approximation method proposed by Dr. Yu, and this actually helped to characterize the quantization error due to the feedback. The remaining parts are the derivations. So first, we focused on the single-user MLT cases. And according to the single-user MLT criterion, we used the MLT criterion, which is designed by the conjugate of the desired channel H1. And this SIR ratio consists of desired signal power divided by the out-of-cell interference. We first drive the ergodic downlink spectral efficiency with a function of pathloss exponent beta and the feedback bits B and the number of antenna N. This blue dashed line means actually the desired signal power, and this red dashed line means the out-of-cell interference. And now we perform the optimization, and we found that the closed form lower bound that actually it fits very tightly with the actual optimum feedback bits obtained by the simulations. And also, we also found that when channel coherence time increases, this pretty complicated term becomes this very nice form, which consists of the number of antenna N and the logarithmically of channel coherence time. We want to introduce some implication of a theorem 1. Why the pathloss exponent does not affect? So actually, in the single-user MLT cases, the feedback is used to boost up the desired signal power. And when we rewriting the SIR of the single-user MLT cases, we can approximate by these cases, because we use the by using the high SIR approximations. This high SIR approximation works well because we use the MLT, and MLT enhance the desired power, so our SIR is rather increased. And this can be divided by this and this by nature of the logarithm, and these effects of feedback bits B and the pathloss exponent beta are linearly separated, thereby no beta term in this derivative. Therefore, the optimum feedback rate is not a function of pathloss exponent beta in the single-user MLT cases. Now we focus on the multi-user forcing. And unlike the single-user MLT, now this signal-to-interference ratio consists of 3 terms, which are the desired signal power divided by the sum of user interference and out-of-cell interferences. So this blue dashed line implies the desired signal power, and this green dashed line means the inter-user interference, which is not perfectly nullified by because of the using of only limited feedback. And this red dashed line means the out-of-cell interferences. So each of these can be found in this integral term. Similar to the MLT cases, we now perform the optimization to find the optimal feedback rate, and we also found the tight lower bound, and we also performed the approximation, and we now found that this, unlike the single-user MLT cases, this pathloss exponent appear in the optimal feedback rate. Now, we now introduce why. In multi-user zero forcing cases, there are 2 terms of interference. First is the inter-user interference, and the second is the out-of-cell interference. When pathloss exponent beta is large, the inter-user interference it becomes a dominant factor to determine the effective SIR. And then because of this, mitigating the inter-region interference significantly improves the downlink spectral efficiency. Therefore, feedback efficiency increases. This means that this encourages to increase the feedback bit. Therefore, this pathloss is going to appear in the linear term in the pathloss, the optimal feedback rate. Here's the summary. We found two new criterion of limited feedback. The first one is a singular MRT cases. The singular MRT cases, it scales linearly with the number of antenna and logarithmically with the channel coherence time. 0% cases is similar, but additionally, it also scales linearly with the pathloss exponent. So ongoing work includes the system level analysis for MIMO headnet with limited feedback and also coordinate improvement with limited headnet. This ends my talk. Thanks.